Good evening. My name is Kabachungo Lindsay, and I will be taking us through feature matching in computer vision. Let me just share my screen and we begin. Okay, so yeah, our topic is feature matching with computer vision. As we probably know, our project is facial makeup matching, and we're going to have to implement some of these algorithms in our code, in our project, because yeah, we're going to have facial recognition and all of that involved. So I will be explaining the first bit and then my colleague will explain the next bits. So what is feature matching? Feature matching is a computer vision process for finding corresponding key points between images. It's used to identify same physical points, stroke objects across different images, and it's critical for object recognition, image alignment, and 3D reconstruction and motion tracking. So why we shall need this? Um, well, our project is supposed to get inputs of someone's image, someone's face, and then we give them outputs of the makeup that would be best for their face based of the features they have. But the only way we can be able to do that is if we have this algorithm implemented. Because let's imagine like if we don't have this, they might probably put a lipstick on the eyes. That's because they haven't, recognized the features or the depths or all that stuff combined. So yeah, this is why it's very important. So there are key points, and these key points are distinctive image features, um, such as corners, edges, blobs, or regions with significant intensity changes that can be reliably identified in different images. So let me say corners, you can take corners of buildings, but for us, let's say corners like cheekbones, um, depth like the depth of the eyes, how the nose comes on the bridge, that can be a corner as well, how the lips bulge out a bit, that could be a blob or a significant area on the face. So yeah, even if those images have probably, even if someone has probably taken the image in a different angle, or if the image is uploaded in a rotated way, this feature should be able to recognize that, oh, this is still a nose, this is still a cheekbone, this is still an eye, this is still lips. So this is why it's also very important. That's why we're going into depth with it. So the primary goal is to identify the same physical features or objects across the different, yeah. Let me go to the next page. So the key properties of feature matching. The key properties of features, they must be distinctive, hence, i.e., stable and unique across different images. Eyes, nose, lips, everyone has distinct features of those. Invariant, it has to be detectable despite of rotation and scaling. Let's say the image is in landscape. You took it as a portrait. Now it's in a landscape. You should still be able to tell that this is a cheekbone. You should still be able to tell these are lips in whichever format it is. Is it reliable? So this should be consistent across different viewing conditions. So examples are building corners, windows edges, door frames, all that stuff. So how it works, uh so how the process is or how feature matching works, it involves detecting the key points. That's step one that we are going to take you through. So we have to detect the key points, the areas of interest in an image. For example, our research point where our reference point, we're publishing about corners of buildings, edges of blobs, all that stuff, associated with descriptions. But for us now, our distinct points, our key points are going to be probably the nose, the eyes, eyebrows, the lips, the face shape, all that stuff, the edges. The edge of our shape will be the face shape, all that stuff. And then, so these key points represent unique and informative, distinct features. Then, we shall have we shall have to describe it computationally, these key points. And then the next step will be description matching, that we shall all explain later, and then match filtering. Yes. So we're now going to go through the popular feature detectors. So we have SIFT, FAST, and ORB. SIFT is scale invariant feature transform. FAST is features from accelerated segmented tests. ORB is oriented fast and rotated brief. So each of these have unique strengths and use cases that I'll explain in a bit. But all these are the forms in which we can do feature detection and all that. But I think the major ones that we shall probably look into are SIFT and FAST. But we shall still explain all of them as of their preference note. For scale invariant features. So let me first try to explain it before I read this. It detects key points by identifying areas of the image that have distinct local structure. So this is done by applying a Gaussian filter at different scales to blur the image. So it first blurs the image and turns it into black and white or grayscale. So by applying this, uh, so to blur the image and then finding the extrema in the differences of the Gaussian. So when you blur it and yeah, the idea is that the edges, the blobs, and the corners remain prominent across different levels of blur, which makes them good candidates for key points. So when you blur the image, still these distinct edges shall still be significant, and we shall be able to detect them as the key point. Yes. So it makes them good candidates. So SIFT key points are invariant to scaling, to translation, and rotation. However much you rotate the image, however much you change its format, however much you reduce or increase the image, scale, invariant, feature transform will still detect these key points that it already did. It will still tell that similarity of these images. It will still be able to um yeah, be able to detect the features and recognize that this is the same as this feature is this in this image, even if any changes are made in different sizes or orientations. So yeah, now let me just read what's here. So it uses Gaussian filters at different scales and then finds extrema in differences of Gaussians and it's invariant to scale, translation, and rotation. So it's highly reliable, but it's computationally intensive, yes. Because when you go into the next step, they call it computational detection, I think, yes. Um, there is a lot that's involved, so yeah, it can be intensive, but it's highly reliable because there's no error. once the image is changed, once the format is changed, there's still detection. It will be accurate. So, yeah, from this image, we can see this is an image that we got. They can locate the facial landmarks, you can see the eyes, the eyebrows, the nose, all that stuff. And then here it divides the page into 16. Okay, we shall get there. Let me just leave this here. So my colleague will explain the code, the scope of code. I mean, I'll just go into depth with the theoretical explanations. So first, which is features from accelerated segmented text. So this detects corners in an image by analyzing the pixel intensity in a circular pattern around a candidate's pixel. So if many circular images are got around a particular area, like if one is here, one is here, one is here, then that algorithm will detect that this is a what? This is a significant key point, and it will mark it as a key point. So yeah, as you can see in this image here, the circular thing is, and yeah. So yeah, the central pixel is marked as a corner. So fast is one of the fastest detectors and works well when only corners are needed as key points. It's a good one. I'd forgotten about that. However, it lacks scale and orientation invariance by itself. Yeah. So if the image is changed, if its format is changed, if its size, if if the quality, if all that stuff changes, this features from accelerated segment test has issues with. So yeah. So basically what's here, it analyzes pixel intensities in circular patterns, identifies corners based on intensity differences. Advantages, it's very fast processing, efficient, and it's efficient for real-time applications. But its limitation, it lacks skill and orientation invariance. That's a difference it has with it has with SIFT, scale invariant feature transform. That's the only difference they have. And this is the problem that FAST has. My colleague will, I think, take us through ORB detectors. Or, let me just take us through ORB detector. So ORB detector is a feature key point detection and description algorithm. It combines fast and brief descriptors with several modifications. It's like a modification of fast in that this withstands the scale invariations. Yeah, so it's like a modernized, it's a developed version of fast. So it uses fast to detect key points and then applies an algorithm. They called it Harris corner measures to retain the only top n key points. I don't want to go through that because I feel like my time is done. So to handle images at different scale, it uses an image pyramid to detect features across multiple levels. Yes. And then a key limitation of fast is it lacks location invariance. Yes, I said that. So this ORB overcomes this by calculating the orientation of each key point. This is done by finding the intensity weight of these pixels. Very smart. And then and it's done by finding the intensity weight of this centroid patch around the key point using the direction from the key point to the centroid, and it assigned to the orientation. So yeah, I basically added some images here to explain how that would be most easily explain. So you can see even after the image is rotated, it was still, you can see from the color code, this blue showing that was on the lip, it still shows that, oh, when it's rotated, it's still gonna be a lip. So yeah, that's it. Thank you. That's where I will end for now, and my colleague will continue from there.
Hello, my name is Kalunji Edward, and I'll be continuing from where my colleague stopped by explaining the code snippets. So that if we are using the Swift to detect the key features, first we have to use the Open CV library, and here we import the CV2, and then we load the image in color using image equals to cv2.imread, and then the name of the image. And then after that, we convert the image to grayscale. That is gray equals to cv2.cvt color, and it takes in arguments of the image and then the cv2.color from blue, green, blue to gray. And then we initiate the Swift detector by using Swift is equal to cv2.swift.create, and then we detect the key points using the key points equal to swift.detect gray, and then none. And then after that, we draw only the subset of key points. For example, the first 50 key points. So key points subset equals to key points up to 50. And after this, we draw the selected key points on the original image. That is image with key points .cv2. So this is the algorithm. Now this is the code for the Swift algorithm, how it works. Next. The next slide. And then when we want to implement the OBR, ORB, first we initiate the ORB detector by using the cv2.orb.create. And then here we detect the key points and compute for this descriptors. The key points descriptors equal to orb.detect and compute. And then step 3 is that select two specific key points. First, the two key points as an example. This is key points subsets equals to key points up to the second. And then also the descriptor subsets up to the second. And then we draw the selected key points on the original image. That is with the image with key points cv2.draw key points, image and key subsets. And then we add the labels on the key points. We loop over each key point and add a label to its location. That's the code for it. And then we create a label for each key point. Next slide. And then here I'll be explaining understanding descriptors. So a descriptor is a mathematical representation, usually a vector that describes the local appearance around each key point in an image. Descriptors are computed after detecting key points and encode information about the surrounding pixel intensities or patterns in a way that is robust and to various transformations such as scale rotation and illumination changes. What are the key points tell us where the interesting points in an image are. descriptors help us to understand what these key points look like. So descriptors are crucial for key points, for comparing key points across different images, which allows us to match the corresponding features, which helps us to match the corresponding features. So it's descriptors help in the following to summarize local images. Information descriptors encode information about the appearance of the pixels around a key point in a compact vector or a binary string. And then next slide, I'll be talking about comparing descriptors using SIFT. So SIFT calculates descriptors by analyzing the local gradients, change in pixel intensity around each key point. A 16 by 16 patch of pixels around the key point is divided into 4 by 4 subregions, and for each subregion, a histogram of 8 orientation is created. This results in 16 histograms with 8 bins each, producing a 128-dimensional descriptor. The descriptor is then normalized to enhance robustness against lighting and contrast changes. The SIFT descriptor is invariant to scale, rotation, and illumination, making it effective for matching key points across the transformed images. And then next, I'll be talking about the descriptors using ORB. So using ORB uses brief descriptors for key points, but since brief doesn't work well with rotation, ORB adjusts the brief descriptors to match the orientation of the key points. When a key point's orientation is calculated, ORB rotates the brief pattern, a set of binary comparisons between the pixel pairs, by the same angle, ensuring that the descriptor is aligned with the key point's rotation. ORB breaks the rotation angle into small increments, and this is 12 degrees, and pre-computes rotated brief patterns for efficiency. A good descriptor needs to be discriminative, meaning that it should be able to distinguish between different features. Brief is effective because each of its brief binary comparisons bits has a high invariability and a mean value near 0.5, making it more likely to differentiate between different key points. However, when brief is rotated, it loses some of these qualities. To maintain high discrimination, ORB searches through the possible binary sets to select those that maintain the high variance. And then next, I'll be talking about matching descriptors. And here we use some algorithms. Here we can use the brute force. We can use the k-nearest neighbors. We can use flan-based matching and locality-sensitive hashing. So first, I'll talk about the brute force. So brute force matching method compares each descriptor in one image with every descriptor in the other image. A distance metric like the Euclidean distance for float descriptors like Swift descriptor, or Hamming distance for binary descriptors like the ORB descriptor, is used to measure the similarity between the descriptors. Brute force matching is straightforward and reliable but computationally expensive, especially for large images or a high number of key points. It compares each descriptor in image 1 with descriptors in image 2 and finds the single best match based on a distance. And next, I'll be talking about KNN. This is the k nearest. The k nearest matching. Brute force matching provides the KNN matching via the BF matcher dot KNN match to get the K best matches. Here, instead of returning just the best match, it returns K best matches for each descriptor. For each descriptor in the first image, KNN finds the top K nearest descriptors for the second image. K is usually set to 2 so that 2 nearest matches are retrieved. This allows us to apply filtering techniques like the Lowe's ratio test to refine the matching and reduce incorrect matches. It compares each descriptor in image 1 with descriptors in image 2 and finds the k-best matches. And then I'll also talk about the FLAN matching. So FLAN, or the first library for approximate nearest neighbors, is an optimized algorithm designed to quickly find appropriate nearest neighbors in the large datasets. FLAN is used for fast feature matching instead of comparing each descriptor from one image to every other descriptor in another. As brute force matching does, FLAN uses effective data structures like the KD trees for floating point descriptors and locality sensitive hashing for binary descriptors like ORB. And then I also finally talk about the LSH, or the locality sensitive hashing. Okay. So to explain the LSH, is a technique designed for binary descriptors generated by ORB or brief. It hashes similar data points into the same buckets, ensuring that points that are close together in the original space have a high probability of being hashed into the same bucket. This makes it effective for fast nearest neighbor searches in binary spaces, providing approximate but very efficient matching. Yes. Then finally I'll talk about match filtering. This is essential for removing false positives. It's also common techniques that we use. We have Lowe's ratio test, cross-checking, ransack for geometric verification. Next slide. And then how we implement the feature marking in computer vision. We have object recognition. This is to be able to identify what type of image it is. Image stitching, like if we have two images that are similar, we can put them together using the image stitching. And then 3D reconstruction. If we had images of a building before, and then the building, let me say, gets a challenge, we can use the 3D reconstruction using this feature matching to reconstruct the original picture of the image. And then we also have motion tracking. It can be used to identify, let me say, a person and then track their movements because we have the key features. And then also augmented reality to recreate some images that are in the augmented world, where we can get their features, the key points, and use them to recreate the images. And then the best practices here, we choose a detector or a descriptor based on the application needs. Consider the speed and the accuracy trade-offs, implement proper matching filters, and then test with varied conditions. And then the feature trends in this area, we have the deep learning based feature matching, improved efficiency for mobile applications, integration with other computer vision techniques, and then enhanced robustness to extreme conditions. And then thank you for listening, watching.